control valves in process control systems. Why control valves exist and what they really do. In any industrial process, chemical, oil and gas, power, water, pharmaceuticals, the control valve is where abstract control logic finally becomes physical action. Sensors may measure, controllers may calculate, but nothing in the process actually changes until a valve moves. That is why control valves are called the final control element, and why, in practice, they dominate real-world loop behavior far more than controllers or algorithms ever do. Control valve as the final control element. Control valve's role in closed-loop control. A closed-loop control system exists to continuously reduce the difference between a process variable, PV, and a set point, SP. The control valve is the mechanism that enforces this correction on the process. In engineering terms, the valve converts a controller output signal, pneumatic or electrical, into mechanical motion, modulates energy or material flow into the process, directly alters the process dynamics, mass balance, energy balance, momentum balance. If the valve does not move accurately, quickly, and repeatably, the loop becomes unstable or sluggish regardless of how well the controller is tuned. From a design perspective, the control valve must provide the correct authority over the process, respond predictably across the entire operating range, remain stable under varying pressure, temperature, and flow conditions. A control loop can tolerate moderate sensor noise or controller imperfection. It cannot tolerate a poorly behaving valve. Difference between control valve and isolation valve. Although they may look similar mechanically, control valves and isolation valves serve fundamentally different purposes. Control valve, designed for continuous throttling, operates at intermediate positions for long durations, characterized by flow coefficients, CV, inherent characteristics, linear, equal percent, quick opening, designed to handle erosion, cavitation, flashing, noise, requires precise positioning and feedback. Isolation valve, designed for binary operation, fully open or fully closed, used for safety, maintenance, or process segregation, not designed for fine positioning or throttling, typically no position feedback or control accuracy requirements. Using an isolation valve as a control valve leads to poor controllability, severe trim damage, unstable loops, premature valve failure. From a process control standpoint, confusing these two is one of the most common and costly design errors. Why valves dominate loop performance more than controllers? In theory, control performance is dictated by control algorithms. In reality, it is dictated by valve behavior. Key reasons: valves introduce nonlinearities, deadband, hysteresis, stiction. Flow through a valve depends on process pressure conditions, not just valve position. Mechanical friction and wear change valve behavior over time. Actuator limitations, cap speed and resolution. A perfectly tuned controller cannot compensate for a valve that does not respond to small signal changes, a valve size too large, low resolution at normal operating range, a valve operating near shutoff or wide open continuously. Practically, the valve defines the minimum achievable control error, the maximum response speed, the stability margin of the loop. This is why experienced control engineers spend more time selecting and diagnosing valves than retuning controllers. Relationship between process variability and valve behavior. Process variability is not only caused by disturbances, it is often amplified or created by the valve itself. Valve-related contributors to variability include stick-slip motion causing oscillations, poor rangeability leading to stepwise flow changes, pressure recovery effects causing cavitation or flashing, valve gain changing with operating point. From a systems view, high valve gain, fast process, oscillatory behavior, low valve gain plus slow process, sluggish response, variable valve gain, inconsistent control quality across load ranges. Thus, valve behavior and process dynamics are inseparable. The valve is not just part of the loop, it shapes the loop. Control loop interaction. Controller output, positioner, actuator, valve travel. A control valve is not a single component but a control chain. 1. Controller output, electrical 420 milliamps or pneumatic signal representing desired valve position. 2. Positioner interprets controller signal and compares it with actual valve position. Corrects deviations rapidly to ensure accurate positioning. 3. Actuator converts signal energy into mechanical force, must overcome process forces, friction, and seating loads. 4. Valve trim and body physically restricts or allows flow based on travel. Each link introduces dynamics, delays, and nonlinearities. A problem anywhere in this chain appears as poor control, even if the controller itself is flawless. Static versus dynamic behavior in real processes. Static behavior concerns steady-state relationships. Valve position versus flow, CV versus opening, installed characteristic versus inherent characteristic. Dynamic behavior concerns time-dependent effects, actuator speed, positioner response time, valve dead time, process lag. Design engineers often focus on static sizing and ignore dynamics. In practice, dynamic mismatch causes oscillations. Slow actuators degrade fast loops. Aggressive positioners can destabilize sensitive processes. A valve that is correctly sized, statically but dynamically mismatched, will still fail operationally. Why valves cause 30 to 60% of loop problems. This statistic persists across industries because valves combine mechanical, fluid, and control complexities. Engineering reasons include wear-induced friction increasing over time, incorrect valve sizing during design, inadequate actuator thrust margins, poor positioner tuning or calibration, process condition changes beyond original design envelope. Unlike sensors or controllers, valves physically interact with the process and degrade continuously. Without proper selection, testing, and maintenance, they become the weakest link in the loop. Control objectives from a design perspective. Flow, pressure, temperature, level control. Each control objective imposes distinct demands on valve selection and behavior. Flow control requires predictable valve gain sensitive to pressure variations, often benefits from equal percentage characteristics. Pressure control requires fast response, highly nonlinear near-set point actuator speed and authority are critical. Temperature control, typically slow process dynamics, valve resolution more important than speed. Interaction with heat exchangers amplifies valve nonlinearities. Level control, integrating process valve stability more important than precision, oversizing is especially damaging. Designing valves without regard to the specific control objective leads to chronic loop issues. Regulatory versus optimization control. Regulatory control. Objective, maintain stability. Prioritizes robustness and reliability. Valve must be forgiving and stable. Optimization control. Objective, maximize efficiency or throughput, requires fine resolution and repeatability. Valve must operate smoothly at small signal changes. A valve suitable for regulatory control may be inadequate for optimization tasks, even within the same process. Fast loops versus slow loops, design implications. Fast loops, flow, pressure, demand quick actuator response, require minimal deadband and stiction. Valve dynamics dominate loop tuning. Slow loops, temperature, composition, allow slower actuators, emphasize resolution and stability. Valve sizing errors are magnified over time. Design engineers must match valve dynamics to process speed. Over-designing or under-designing here directly translates to lost control quality and increased operating costs. In process control systems, control valves are not accessories. They are decisive elements. Understanding their behavior from a design, dynamic, and operational perspective is foundational to building loops that actually work in the field, not just on paper. Fundamental valve terminology and construction. Speaking the language of valve engineering. If Module 1 established why control valves dominate loop performance, this module is about how they are physically built and why every construction detail directly affects control quality, reliability, and lifecycle cost. As a design or instrumentation engineer, fluency in valve anatomy and construction is non-negotiable. This is the language that connects process conditions, mechanical integrity, and control behavior. Valve anatomy: body, bonnet, trim, plug, seat, stem. A control valve is a pressure-containing mechanical system with moving internal elements. Each component has a distinct engineering responsibility. Valve body, the primary pressure-retaining shell, defines flow path geometry and pressure drop behavior. Must withstand design pressure, temperature, corrosion, and erosion. Material selection directly affects service life and safety margin. Bonnet provides access to internal parts for maintenance. Supports packing and stem sealing. Influences allowable temperature range and leakage class. Extended bonnets are often required for cryogenic or high-temperature services. Trim, collective term for plug, seat, cage, stem, and internal guiding parts. The functional heart of the control valve determines flow characteristic, noise generation, cavitation resistance, and controllability. Most frequently replaced components due to wear. Plug or disc, the throttling element that modulates flow. Shape defines inherent flow characteristic, linear, equal percentage, quick opening. Subject to high velocity, erosion, and vibration. Seat, the stationary sealing surface, determines shutoff capability and leakage class. Seat material and geometry control wear rate and tightness. Stem, transmits actuator motion to the plug, must maintain alignment, strength, and sealing integrity. Stem finish and straightness critically affect packing friction and hysteresis. From a control standpoint, trim geometry and stem guidance dominate valve precision far more than body material or size. Linear versus rotary motion control valves are broadly classified by how the throttling element moves. Linear motion valves, plug moves axially up-down, common in globe-style valves. High throttling accuracy, better suited for severe service and high-pressure drops. Typically slower, but more stable. Rotary motion valves, disc or ball rotates about a shaft. Used in ball, butterfly, eccentric designs. Faster response and compact design. Higher capacity for a given size. Generally lower inherent precision than linear valves. Design trade-off. Linear equals precision and stability. Rotary equals capacity, speed, compactness. Pressure retaining versus non-pressure retaining parts. From a mechanical integrity perspective, valve components fall into two critical categories: pressure retaining parts, body bonnet joints, end connections. Failure here is a safety event. Non-pressure retaining parts, trim, stem, packing, actuator interface components. Failure here is a performance or reliability issue, not a containment issue. Design engineers must treat these categories differently in material selection, stress analysis, inspection and testing, maintenance planning. Valve body configurations. Globe valves, single port, double port, angle, three-way. Image single port globe valve, one seat and one high pressure drop capability. Excellent shutoff and controllability, higher actuator force required. Double port globe valve, two opposing flow paths, reduced unbalanced forces, lower actuator size, reduced shutoff tightness compared to single port. Angle globe valve 90-degree flow path, reduces piping elbows, effective for erosive or flashing services. Three-way globe valve, mixing or diverting service, used in temperature control applications, requires careful flow path. Analysis to avoid interaction issues. Globe valves remain the benchmark for precision control despite higher costs and size. Rotary valves, ball, butterfly, eccentric disc, eccentric plug. Image ball valves, high-capacity tight shutoff V-port designs to improve throttling performance. Sensitive to erosion and throttling service. Butterfly valves, lightweight and economical for large sizes. High flow capacity, lower pressure recovery performance. Susceptible to non-line arcane at small openings. Eccentric disc valves, offset shaft reduces seat wear. Improved throttling compared to concentric butterfly. Common in large flow applications, eccentric plug valves. Combines rotary motion with plug-style throttling, good compromise. Between globe precision and rotary capacity, effective in dirty or slurry services. Rotary valves are often chosen for economics and footprint, but they demand careful control characterization. Flow direction, flow up versus flow down. Flow direction matters far more than many designers assume. Flow down, process fluid assists closure, lower actuator force, higher risk of plug instability and throttling. Packing sees lower pressure. Flow up, process fluid opposes closure, higher actuator force required, improved stability at partial openings, better seat life in erosive services. Incorrect flow direction selection can lead to vibration, premature trim wear, poor control near set point. End connections and mechanical interfaces. Flanged, threaded, welded, wafer, flangeless. Image flanged, most common in process plants, easy installation and removal, requires gasket management, adds weight and space. Threaded, used for small sizes and low pressure, compact and economical, limited service range, higher leakage risk over time. Welded, permanent, leak-tight installation, preferred for high pressure and hazardous services, maintenance intensive, requires shutdown for removal. Wafer, flangeless, common with butterfly valves, minimal face-to-face dimension, requires precise alignment, load transferred to piping system. Face-to-face dimensions and piping impact. Face-to-face dimension defines how much linear space a valve occupies in a pipeline. Design implications. Affects piping layout and stress. Impacts retrofit feasibility. Influences maintenance access. Determines interchangeability between valve types. Ignoring face-to-face constraints often results in forced piping rework, excessive field modifications, misalignment-induced valve stress. Installation constraints. Engineers must anticipate a control valve does not exist in isolation. It lives inside a mechanical system. Key constraints: straight run requirements upstream and downstream. Access for actuator removal. Clearance for packing maintenance. Orientation limits for actuator weight. Drainability and venting for startup and shutdown. Poor anticipation at design stage leads to valves that are theoretically correct but practically unmaintainable. Module 2 is about mechanical literacy. When you understand valve anatomy and construction deeply, you stop treating valves as catalog items and start treating them as engineered control instruments, which is exactly what they are.